No hard? Easy? That last problem with red balls and white balls, right? They ask you to compute a matrix, right? How about the stationary distribution? I know it's not that what's asking. I'm asking. Is there a stationary distribution? And if not, why not? What kind of Markov chains do not have a stationary distribution? And why would that be? That's just a simple way. Not that simple, but like a quick question for somebody who wants to think about something. So remember that you guys owe me an entropy problem from last week. That's a simple problem, similar to what I've done last time in class on Friday. It will take about 45 minutes or so to work it out in the recitation paper. So we expect those to come back, this week. Next week, there is the next quiz. 30 minutes on probabilities and expectations. There is a new honors problem about binary search trees that we're going to talk about. Usually Thursday nights is when I have office hours for this kind of stuff, but also a little bit of recitation. Binary search trees are very related to what we're starting today as a new chapter. Okay? So once we talk about basic searching and sorting today and tomorrow, at some point we're going to talk about more interesting searching and sorting, which is binary search trees. I think the regular class doesn't do binary search trees. That's part of the algorithms material that you guys take the second year. But we're going to do a quick introduction, which is not a fancy thing. Okay, so that's the plan. Before I start this, I can't let go of the distributions and expectations, so I still have about 10 minutes of showing you something about that. Which is kind of a moral point recap of what we've done. I won't go into math, but I will do this. So, random variable, you look at x values and x probabilities. And you have like some sort of table where it says here's x1, probability of x equals x1, x2, probability x equal x2. And how many values are there? Say the last one, xn, probability of x equal xn. I think everybody knows this by now. If I have a die, those are 1, 2, 3, 4, 5, 6 the faces, and those are the probability to see those faces, which could be uniform if the die is a normal uniform die, or not. If it's a fake die, maybe 6 has a large probability of showing up. In fact, that's how people fake the die. They make 6 more likely. Right? And if we have 2 variables, right? We have x and y, and then we start having different. My point I want to make today is that a lot of stuff comes from this table, conceptual. So what is the expected value? Is the sum of xi times probability x equal xi. Right? Sum average the values weighted by the probabilities. What is the variance? Is the sum, again, overall values. We take the value minus the expectation squared, and we divide by how many they are if it's uniform. If not, we multiply with the probability. Multiplying with probability in a uniform case is the same as summing them up and dividing by how many they are. Because in a uniform case, you multiply with 1 over n. So uniform means P of x, xi is 1 over n, which is equally likely over all the parts. Finally, the entropy is sum overall values of P of xi logarithm, typically base 2 of 1 over P of xi. P of xi means the same as P. So this is the same as P of x2. When we short notation, when we say x equal x2, it's the same as when we say P of x2. So my point is, you're gonna see a lot of this stuff in your scientific life, even as non-computer scientists. What this is called here, this is called a distribution. This part. This is the space, the values. What can it be? 1, 2, 3, 4, 5, 6. Heads or tails. Student names, shapes, objects, IDs, colors. This is the distribution. This is saying how likely is X to take each value. The distribution of things, it's one is a theoretical distribution, what you see, and one is empirical. If I don't know this variable, I could pick a sample, roll the die, right? Remember last time I ran the simulator that rolls a die? That's the empirical distribution, which if I don't know the actual distribution of a die, I can roll it 1,000,000 times and count how many ones, how many twos, how many threes, how many sixes I see. And if that's roughly uniform, I'll say probably the die is not modified, it's a uniform die. Same thing with the coin. If I want to know if the coin is fair or not, I toss it in the air, and if I see equal number of heads and tails, that's the empirical distribution, the observed distribution. I'll say probably this coin is 50-50. Right? You're going to see a lot of this. A lot of the world principles, machinery, and money, let me emphasize that, money works by knowing distributions and understanding distributions. A lot of people who make money rely on some mathematician down the line who understands distributions. Stock market, it's all about distributions. Patients, diseases, recoveries, drugs, success, failures, all about understanding the distributions. Weather predictions, all about distributions. People chance at, say, running over the T stations and catching the train. It's about understanding the distributions. The expected return for your investment, retirement, guess what that's about? It's understanding the distribution, right? Chances to get into a car accident, it's a distribution. Chances to get, recover after a car accident, that's a distribution. Chances to, go skiing and break your leg, that's a distribution. Okay? A lot of the things that are not clearly determined are about understanding a distribution. Now, these three things are statistics based on a distribution. But like I showed you in class, remember when I did 3 dice, one was fair, one was 1 and 6s, one is 3 and 4s? They may have the same kind of properties, but not exactly the same distribution. So you can get the same mean for different distributions. You can get the same variance for different distributions. Even the same entropy for different distributions. So if you want to fully understand what's going on with the process, data science is a sampling, a drug, a patient, you got to look at the distributions. That's why in those studies, epidemiology studies, medical studies, social studies, Facebook studies, they study the distribution of things, not just the mean and the variance. Remember the problem I did with the infinite expected return in recitation? We had that return, b pays a 2 to the k, where k was the number of throws. We looked at its expected, we say that's infinity. Somebody pointed out that if expected is infinity, variance must be infinity. Because if this guy here is infinity, I'll get infinity. We can also look at the entropy. But the right thing to do for a casino that plays a game or a lottery is to look at the full distribution. What are the possibilities? How this is going to play out? Economists, especially macroeconomists, the people responsible for federal bank, lowering the rates, the federal rates, or increasing the rates, they gotta look at the distribution over a lot of possibilities and historically about what happened to determine we need to increase or decrease the rates. It's all about risk assessment. If you want to know what is the risk, you're a bank and you have to give loans to people. How do you determine to give a loan? Of course, there is a process with scoring and credits and the income and all that, but it comes down to a distribution. What is the likelihood that this person can pay, for how long, how much, so on and so forth. So, in a lot of cases, you're gonna have to deal with the actual distribution if you want to succeed. And empirically, we do sampling. If we don't know the theoretical distribution, we look at all the patients we have and say how many of those people have severe diabetes, how many of these people have Zika, or so on and so forth. It doesn't mean we know the exact distribution, but we can sample and make an estimate from the sample. And we're going to see a lot of histograms. That is, they have to do with, you see what you observe. Those are the values, say xi, and these are the frequencies or counts, which is approximately phi of xi. Right? The more we see something, the more likely it is to happen. And we're going to see some distribution. This is a histogram that if the value is discrete, say for a die 1, 2, 3, 4, 5, and 6, we see the kind of histogram I showed you yesterday when I did, not yesterday, that was on Monday, but last time was Friday. We saw counts, right? How many times I see a 1, how many times I see a 2, 3, 4, 5, and 6. This would be a non-uniform die. If I roll the die 1,000,000 times and I see a lot more 6s than 5s, 4, there's a strong chance that this die was not uniform to start with. I still don't know its exact distribution, but the more I throw the die in the air, the more this will be closer and closer to the actual distribution. That's the law of large numbers that says you can't throw this die 10 billion times in the air and get very different estimated distribution than the true one. That's a mathematical theorem that says if you throw enough times, the probability of getting far away from the true distribution becomes very, very small. So you got to get used to the notion of a histogram. If you look at patients, or you look at pollution, or you look at weather patterns, you're going to see a lot of empirical data which has to be plotted. Finally, I show you something that I want to describe today in more detail, just for the purpose of finishing it. How about the continuous random variable? So all the random variables we talked about were discrete. They have this value or that value or that value. So for a die, there were 6 values. For a coin, there were 2 values. For 2 dice, the minimum was what? 2 when you sum it up, and the maximum was, if I sum up 2 die, what do I get? 12, right? So it's 2, 3, 4, 5, 6, up to 12, right? And all the problems you've seen have discrete. How many diamonds can you extract from a bag? Well, there's so many possibilities. 1 diamond, 2 diamonds, 7 diamonds. But what if I have a continuous space? What if my histogram, so to speak, looks like this? Is any value is possible in here. So this is from like minus infinity to plus infinity. Every single value is possible. It's not like it's either, like you see how this plot is, you can't roll a die and get the 4.3. It's either a 4 or a 5. But you could have a variable that takes every value on the real numbers, right? For example, I don't know, time could be, or amount of water in a pipe or something like that. That could be a continuous variable. So I have a continuous space, but I still want to measure something like frequency in here, and this is values. Clearly, that's not going to look like a pixelated 6 dots or 8 dots or 12 dots. That's going to look like a line. And the distributions we can model mathematically have to be nice continuous lines. If it's something completely random on the real axis support, this is the real axis, any number is possible as a value. We can't have discrete random values. So the distribution I want to show you is the Gaussian distribution, also called normal, also called the belt. It looks like this. It's symmetric, even though mine is not that symmetric. And it has a mean, so this mu, that's the expected value of x. And it has a variance, of course, just like a discrete distribution. So variance typically it's notated, it's marked like this. So pick a value here. This is x, right? A value. What do we mean by the probability this is x? Clearly, this is not a uniform variable, right? Because some things in here are very unlikely, and some things in here are very likely. Remember the meaning of a histogram? The higher the bar, the more likely it is. So there is a formula for this. It's gonna be scary if you haven't seen it yet. So here's the formula. It's 1 over 2 pi sigma squared inside the square root. E at the power x minus mu squared divided by 2. How many people have seen this formula before? Hands up. Or have seen something like this formula. So how does this work? First of all, this is a constant. Don't worry about what it is. It's just a constant. And this is what governs the line, right? Because this is an exponential, we're going to deal with this dude later, who this is. I know you know it's about 2.7 something, right? But anybody knows what he actually is? Not the approximation, but what is this number? We'll deal with that later, part of this chapter. But it's an exponential, and it's a negative, so what's going to be the highest value of an exponential? Clearly, x minus mu squared is a positive value. So this whole thing is a negative value. So out of all exponential e at a negative, what's the highest value? E at what? So again, let me pose this question again. This thing here is a square, so that's a positive thing. With a minus, that's a negative thing. How do exponential react to the actual exponent? The highest value is where? Yes.
When it's 0.
When it's 0. So when is this guy 0?
When you're at the mean.
When x is mu, right? That's where the 0 happens. So at the mean, it's the highest. This is e at 0 in this point, right? What is this value here? Is 1 over 2 pi sigma squared, right? Times e at 0. That's what it is. Because when x is exactly mu here, I get a 0 here. And as far as this moves, the x, my variable, moves away from mu, this becomes negative. So e at something becomes smaller and smaller and smaller. And you can see why it's symmetric. It has the same effect left side or right side. Because x minus mu, it doesn't depend whether x is on this side or x is on that side. X minus mu squared will be the same on either side. Hands up is with me so far. Perfect. All right. I'm not worried about this formula. Although this formula has profound impact in a lot of mathematics and physics. So this exact formula, why it's like this and not some other exponential with some other form. It's, you know, like you can imagine a lot of continuous functions that would give you some distribution. Why it's that one? It has very important property in terms of, say, entropy, in terms of natural processes, so on and so forth. But we're not worried with the formula right now. The first thing we have to understand, which is something we can understand today, is this is a continuous random variable. It can take any possible value here. Well, this is a discrete random variable. It can only take 1 or 2 or 3 or 4, 5, 6. Therefore, in a discrete random variable, I'm going to say sum of all the probabilities for all values must be what? In a distribution, if I sum, must give 1. Can I say the same thing in here? Can I say the sum over all values, real numbers, p of x equal xi is 1? That will be impossible, right? How many values are in here? How many values are in here?
A lot.
Exactly how many? Is it a finite number of values or an infinite number of values? It's an infinite number of values. And all of them have some probability, right? A little bit of probability, or more probability, or a little bit of probability. If I sum an infinite numbers that have probabilities of some size, what would I get? I have a sum of infinite number of values. And each of them has some probability, at least blank. How much would be that sum? Again, I sum up infinite number of values, and each of them is at least, say, 0.0001. How much is the sum? If I sum an infinite number of things, and each of them is at least 0, how much is infinite times, say, 0.000001? If I sum up this value infinite number of times, what do I get? Infinite, right? Any positive constant that multiply with infinity is going to be infinity. So that's infinity. Clearly, this doesn't work. Right? You cannot, in a continuous domain, sum over every single value because it's not just infinite number of values. Just the natural numbers will be infinity, right? There is someone here 1 or 2 or 3 or 4 or 5. And so on and so forth. Even if I sum up just the natural numbers, which is still infinite many, but a discrete. There's nothing in between the natural numbers. Even that will be infinity. Let alone if I sum up every single thing in between the natural numbers. So how do I take this, which makes total sense, right? One has to do with being a whole. Everything has to be of some kind, right? When you pick a shape, object has to have a color. When you pick somebody, it has to have a name. When you pick a patient, it must be either that way or that way. It makes sense to say sums to one, as in everything is of one kind. How do I do that here?
Well, you could say each value has, or you could say each point on your real number line has some value, right? And you can have some kind of infinite sum. And then if you take the limit of that infinite sum, you're going to throw some value.
I don't need to do a limit. I like the way you think, but the limit is not the process of how many things I sum. You know, limit has to do with if you sum 2 of them, you get that. If you sum 3 of them, you get that. 4 of them, 5 of them, 6 of them, n of them, 100 of them, 1,000 of them. The more you sum, the more something happens. That's a limit. In here, I sum up all of them from the beginning. The problem is this sum doesn't generalize this property, sum over all values. You can't do that in here. I need a different kind of sum analogy in a continuous space. I can't do a sum. Because sum will always be infinity. It's sum of the infinity things. What do I need?
Could you use an integral?
Yes. I need an integral. From where to where? An R means from minus infinity to plus infinity, right? And in integral, sometimes we say dx in here. I mean, this is a notation, if you remember from calculus. I don't want to worry today about integrals. I want to point out that if my variable is continuous, I can't use summations. I have to use the analogous of summations in the continuous space, which is the integral. Some of you have seen integrals, I'm sure. And as an exercise, somebody can integrate this function and show that it's indeed 1. In fact, every distribution in continuous space must integrate to 1 to be a distribution, just like any distribution in the discrete space must sum to 1 to be a distribution. So any continuous distribution, Poisson, exponentials, beta distributions, gamma distributions, student distributions, anything has to integrate to 1 to be a correct distribution. But then, the chance, if you compute this value and you get a number, you can't say, since this number is, say, I don't know, 0.12, 12% of the time is going to be that value, because that's not how it works, right? So I don't want to do anything with continuous distributions. I just want to show it to you. So if you ever see a continuous random variable before you take advanced calculus, you know that it's exactly the same thing with an integral instead of a sum. The last thing I want to show you about this distribution is because it's so natural. We talked about this last time. The reason it's natural is because a lot of the things in practice come from summations. Think about your midterm score. Is it a summation, your midterm score? Is it going to be a sum of things? What things? Right. Think about your credit score. Is that going to be a sum of things? Yeah. Think about your GPA. Is that the sum or an average of things? Yeah. A lot of things that you see in nature are actually a sum of some other things. And what we did on Friday was show if you sum enough random variables, or if you average them, that average is going to start looking Gaussian. It doesn't matter whether the original distributions of patients or diseases or problems, it's not Gaussian. When you start averaging a lot of things, you get Gaussian distributions. That's why this appears so often in practice, because in practice, things come from a sum or average, most of the time. So then, I want to give you a representation of variance. An intuition. I don't want to do math, just an intuition. This is standard deviation. That's just the name. And it's the square root of variance. That's why we call the variance sigma squared, to take the square root and get the deviation. So these, for Gaussian distributions, I'm going to show you how to think of this standard deviation, which is not a variance, it's the square root of variance, but without math. I'm going to say, here's the mu, the expected value. That's the mean. By the way, who's going to be the mean then? If can I do the mean this way? In a continuous space? Can I sum up raw value times probability? No, but what am I going to do instead? I'm going to do an integral of value times probability. And this integral, it's going to be exactly the center of the Gaussian. Because this is symmetric, positive and negative sign. Here's what happens if I move one standard deviation away from the mean. This is x minus some standard deviation, and this is x plus a standard deviation. What we want to call here is say, okay, between those two guys, we have one standard deviation, or one STD, we can call it.
Come on.
In a Gaussian, the area under this area here is a fixed proportion of the Gaussian mass. Anybody knows what is this intuitively, visually? I know it's an integral, but what visually, what is it? Yes?
The area of the curve.
Is the area under this curve. Like geometrically, that area has to be 1, right? What is this saying? One standard deviation plus minus, it's about 68%. One sigma, 68%. So if something is distributed Gaussian, say the grade on the meter, it has a mean, and we say the grade distribution is Gaussian. How many students will have a grade about within one standard deviation of the mean? So not lower than one standard deviation, not higher than one standard deviation. How many students will have a grade close enough to the mean within one standard deviation? 68% of the students, if the grades are distributed Gaussian. Of course, this depends on the actual standard deviation variance. With a small standard deviation, that 68%, it's still 68%, but it's close to the mean. In a large variance, it's still 68%, but could be farther from the mean. How about two standard deviations? That's 1, 2, so that's x minus 2 sigma and x plus 2 sigma. How much is in here, in between? So this is the middle part. Now I'm adding, say, these parts to it, and these parts to it. That says, how many students, if the grades are Gaussian distributed, how many students are between minus 2 standard deviation to plus 2 standard deviation away from the mean? This whole area here is like 95%. So plus minus 2 standard deviation is 95% of the mass. So because you have to know those numbers 68 and 95, because you're going to deal intuitively with normal distributions, whether it's stock market, numbers, predictions, patients, images, emails, whatever. If it's normally distributed, if you know its variance, you're going to know from the mean and variance alone how many things are within 2 plus minus 2 standard deviation plus standard deviation. That's 95% of all the emails or images or patients that you have. Pretty much all of them. So for a Gaussian, what really matters is what happens between, in practice, minus 2 standard deviation plus 2 standard deviations. Because the rest, which we call the tails, are together. How much are those tails together? 5%? So those could be kind of the exceptions, right? So that's what I want to show you about this. Of course, this is not, from here on, this is not discrete math anymore. This is continuous math. You need a lot of integrals and derivatives and analytical tools to deal with this kind of distributions. But you should know what the normal distribution is, what is its formula, and how the standard deviation works. All right, that's that. So now we're finally ready to move on. I hope you guys had enough of probabilities and expectations and variances. And if you didn't, next week there's a quiz. That's the last encounter. Oh no, there's a final too at some point, right? Yeah. So we're starting a big chapter. This chapter is, like always in this class, a lot of recap from things that you've seen in high school and a lot of new things. And the problem in this chapter, algorithms, function growth, recursive functions, inductions, and let's add series there, series, right? There's a chicken and egg problem. There's no way to start one of these things and finish it without going through the others. So I could start at series. I can't finish series before I do induction and recursions. I could start at algorithms, but I can't really finish algorithms before I do series and induction and recursions. I could start a function growth, again I need induction. I can start with induction, then I need series. And no way to pick one, do it, right? So let's call it a 4 weeks chapter. We start today, and we have 4 weeks to do it. And we're kind of going to build it brick by brick here. We're going to do a little bit of algorithms, then a little bit of series, then we're going to do induction, then we're going to do more algorithms, then more series, then, because that's how we can build it up. But I want to give you first an overview of how that all works. So let's split it into algorithms. We make some columns here. It's a big overview of what's going to happen. Then we need functions. Then we need, say, math. And then we need tools. Math concepts. And math tools. Try to fill this table. So what we have here, we have search. We already done some of it, like linear, chunk search, binary search. I clearly remember we did binary search, for example, when we talk about binary bits and digits. Right? And then those cards from the first week or second week when we hand out the cards that have to do binary search. And then we have sorting. We talked a little bit about sorting, right? I think, did we talk about merge sort? We did a little bit of merge sort, right? We talked about insertion sort? Maybe not. We talked about maybe bubble sort. Did we? I think we just mentioned it when we had something to do with it, but maybe some of you haven't seen bubble sort. Selection sort, maybe we can do that. Anybody heard of Quicksort? Hands up who heard of Quicksort. Hands up who knows how Quicksort works. Hands up who know why Quicksort works, as in a proof.
No.
All right. So that's more like taking one. How about heap sort? There's a lot of sorting ideas. Bucket sort? Anyway, too many. What we want to do though on all this stuff is to do pseudocode. I mean, there is the idea, bubble sort, right? Take a bubble, things that are out of order, and flip them, right? And if you flip all the bubbles, are you done? Is it sorted? Yeah, that's the idea, but how do you actually do it? What's the recipe? Write it up as a procedure so you can implement it in a programming language. And then we have analysis, which is runtime. How long does it take to run insertion sort, bubble sort, binary search, and all of that, right? We have memory. And we have some computer science properties. Like, for example, is it stable? I don't want to say what that is yet. But even though algorithm can be fast and doesn't use that much memory, there's other properties. For example, do you flip two trees, two values that are the same? You don't have to swap them, but some algorithms swap them anyway. So that's called unstable. And then in terms of functions, because of all the things in computer science are pretty much divide and conquer, we're going to have to see what that means. That's going to imply recursive functions. For example, something that looks like this. This equation, T of n is 2 T of n by 2 by n. Obviously, it's a recursive function because the definition relies on itself, on a smaller value of itself. So that says T of 100 is 2 times T of 50 plus 100. This is the recursion. Everybody knows what algorithms have this kind of runtime? Out of all the stuff listed here, there is one that has this runtime. Merge sort. Because merge sort is going to break the things in half and sort them to halves. So that's 2 times merge sort of a half. And the merging part will take linear time. But we need to solve those things. Like that's how it comes out of the algorithm. But what is it? What kind of function is that? And then we need here sequences, numerical sequences. And series, things like 1 plus 2 plus 3 plus n. That's arithmetic, right? 1 square plus 2 square plus 3 square plus n square. That is quadratic. How about r to the 1 plus r to the 2 plus r to the 3 plus r to the n? What is this? Anybody knows that? What kind of series is this? Okay, maybe with the one in front of it. Geometric. We're gonna need, this is basic arithmetics. We're gonna need to know how to do those things in order to calculate stuff. I'm not showing you here how to do them. I'm just saying we're gonna need a lot of formulas and mathematical arithmetics and algebra to figure out how those sums work. How about 1 plus 1 over 2 plus 1 over 3 plus 1 over n? Harmonic. How about, what was that one? 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus 1 over n times n plus 1. Anybody knows how to do this one? It's an exercise for Friday. How do you compute this one? I'm assuming some of you have seen certainly the first one, maybe the second one, maybe the third one, probably not the fourth one, and this is just an exercise, how do you do it? We're also gonna need exponentials, or other exponentials, and logarithms. That is log and base b of n. We're gonna need some math tools. Of course, we're gonna have to have, here's a series, here's how that works, da 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 da. But then we need to do induction with proofs. Again, it's something that some of you have seen, but I'm not counting on that. We'll do induction from scratch. And we're gonna need to do inequalities and approximations. In function analysis here, I'm gonna add the idea that we're gonna have to say, here's some function is linear. What do we mean linear in mathematics? When somebody says in math department, a function is linear, what do they mean? What is a linear function? F of x is ax plus b. That's linear. Yes.
For every x value, or for every x value, there is a unique y value, but also for every y value, there is a unique x value.
That's not linear. That's called one-to-one. That's a bijection. And it could be, bijections are not necessarily linear. Linear functions are bijections. But you can have a quadratic or an exponential function has exactly that. Y equal 2 to the x has the property you say. For every x, there's a unique y. For every y, there's a unique x. But that's not a linear function. Yes. Right. It's a, if you plot it, what do they mean? If you plot x versus f of x, you observe a what? What do I get for that function? For any a and b, yes. What do I get?
It's a straight line because it's constant rate of change.
A straight line. You wanted to say something?
I was going to say the definition of linear is like f of x plus y equals f of x plus f of y.
Right. I don't like that definition.
Well, okay.
That's American definition. I'm from Europe, so I'm not going to use it. Okay? I like these definitions. So whoever is good at math and wants to impress me, this is easy, right? If a function x plus b, would they have this property?
Yeah.
Well, b has to be what?
So, yeah, yes.
How much is f of x? Ax plus b. How much is f of y? Ay plus b. And how much is f of x plus y? Ax plus ay plus b. So the a's work out, right? I have ax here, I have ay here, I have x times x plus y. That works out. How about b's? How many b's are in here? How many b's are in here? Do people follow me what I'm doing here? Can I prove from here to here? I don't think it works unless b is 0. For this to work out, ax plus ay would be x times x plus y. Is this true? A works out, right? Ax, ay, ax, and y. How about b? B doesn't work out. There's one b and two b's here. So the only time this works out is when b is what? 0. So this works out if b is 0. But if you really want to impress me, show the other way. If a function has this property for any x and y, then it must be a times x plus 0. So the only functions that have this property are the functions a times x. So that definition of linear is the same as this. I like this definition, including the fact that b is 0. That has to do with the fact that later on you're going to study machine learning and regressions, and in regression you're always going to have a b. So that's linear. That's the math. But we are computer scientists, and either we're lazy or we are loose mathematically. This is not what we mean by linear. So that's the math department. We walk into the math department, linear means that. What about CS department? So that's the math department. Here's CS department. We should technically call it approximately linear or asymptotically linear. That's the name. Asymptotic linear. But of course, we're very lazy in computer science, so we just call it linear. Right? What do we mean when we say a function f is linear? We mean it's smaller than a function that's actually linear for real, like in math department. And it's bigger than a function that is linear in the math department. That's what we mean by asymptotic linear. There's some function linear bigger than it, and some function linear smaller than it. So of course, you can have a lot of functions now that are not linear at all, but we call them linear anyway. Right? For example, what happens if I put here f of n is n plus square root of n plus 1 over n squared? Is that a linear function? Of course not in the math department. Right? Are we agreeing with that? No mathematician would say that is linear. But is it smaller than a linear function? Sure, 3n. Is it bigger than a linear function? Sure. What function? N. Therefore, it's linear. See? Well, again, correct term is asymptotically linear. Right? But we just whatever. So if we plot this function, if we say here's n, here's f of n, what we care in computer science is where is n? N is the diagonal, right? That's n. Where is 3n? It's a bigger line. 3n is still a line. It's like this, 3n maybe. What do we mean by being linear in between those two? Those 3n, it's a big function like that, right? We mean it's around here somewhere. That's what we mean, right? It's in between two linear functions. Therefore, it's linear. For our purpose, if it's in between two linear functions, linear anyway. The point is here, the square root of n, let me write it nicely here so you can see it. N plus, what did I say? Square root of n plus 1 over n squared. These guys, square root of n, 1 over n squared, are not adding significant amount to it. This guy actually, when n goes big, goes to 0, right? So that's very small. This doesn't go to 0, but it's less than n, and we already have an n. So it's between n and 2n or 3n linear. How about the function? By the way, we call this, the fact that it's linear, we say f is theta of n. That's the notation we have. When we say it's linear in computer science or asymptotically linear, we call it phi of n. N is the linear function. You have to know the intuition here. I'm not going to ask you for exact definition. I'm going to say, if you say something's linear, you got to have a function linear smaller than it and one linear bigger than it.
Are we saying that n is only integer values?
N is what?
N is
No.
only an integer value?
We can say n is integers or not. Doesn't change the property. But we want this property to hold for n goes big. So whether you just use for integers or for all real numbers n, you're going to get the same effect. The important stuff has to happen when n goes to infinity. Yes.
So for small enough real n, it seems like it's not. There's no linear function.
Okay. Starting at some point.
Okay.
He's so picky. I don't want to deal with those details now. But okay, you're right. It's not going to happen in the beginning. Maybe at some point, maybe starting at n, 100 or 50 or 20. It doesn't matter the beginning part. It matters the end. Remember, it has to go to infinity, and it has to start at some point. And all those functions are monotonic functions. So whether you just do integers, or you do rationals, or you do reals, you're going to have the same effect. The point is, what he was just saying, what in the beginning, it goes a little bit up, a little down, a little up, a little down, and then eventually falls in between. Is that still a linear? In the beginning, I went over the bounds, but at some point, I started at n equals 50 in the bounds, and from there, I don't go outside the bounds. That's still linear. We don't care the beginning. We care at some point what's the asymptotic behavior towards infinity. And we call that theta of n. How about a different function? By the way, I have another column here that I didn't get to talk about, but I'll add it later. It's data structures. Finally, something related to the course title, right? I will get to that in a second. Let's take another example. You guys tell me if this is linear or not. So what if I take the function f of n is just the square root of n? Is that linear? Is it square root of n? Is it smaller than some linear function? Do you know a function that's bigger than linear that's square root of n? N. Is it bigger than a linear function?
Yeah.
What?
0.
See, I don't like 0. A has to be positive. Linear, I know technically you can have A equals 0, and in that case, what is this function if A is 0? Which is a constant. So I want to say linear is not constant. I like constants and I like linear functions, but not together. I would like to point out when something is constant versus when it's linear. So, got back to my definition. I don't like A equals 0 here. So I'm not considering that a linear function. That's a constant function, just B, right? Everybody can see that if I plug A equals 0, I get just B all the time. So that's kind of like a flat function. So is there a linear function in here?
No.
Even if I put A very small, like what if I put 0.000000001 times n? Is that going to work?
No.
At some point, initially it's going to work, right? Square root of n equal 2 and 3 and 4 and 5 and 10 and 11 and 100 will definitely be bigger than this, right? Think about 100. How much is square root of 100? How much is this times 100? It's a very small value, right? But at some point, the square root will be smaller than this. Can everybody see that? If this n, say this is 10 to the minus 6, what kind of n will beat the square root so my inequality fails? Yes.
N equals A plus 1. Or n equals...
How about 10 to the 9?
Sure, yeah.
10 to the 9 is how much in here? This part, if n is 10 to the 9, how much 10 to the 9 times 10 to the minus 6? 10 to the 3, and square root of 10 to the 9 would be? Still works or it's broken? Still works. This is bigger than that, but I want to show that it's broken at some point. How about 10 to the 12? How much is the left side? 10 to the 6. How much is the right side? 10 to the 6. This is the breaking point. If I increase n further than 10 to the 12, this will be bigger than that. So the point is, these, even though it look like a small coefficient will do the trick in the beginning, remember it's not the beginning that matters. It's the end. So I could have 10 to the 100. What happens at 10 to the 100? How much is the left side? 10 to the 100 times 10 to the minus 6 is? 10 to the 100 times 10 to the minus 6. 10 to the 94. And how much is the square root of n? Square root of 10 to the 100? 10 to the 50. This is way bigger. So if I go far enough to the infinity side, to the right side, I don't get this to be between the functions. Ends up with the point I'm making here is it looks in the beginning like it might work, but it does not. Asymptotic behavior has to do with the end, not with the beginning. Let's do the same for quadratic functions. What do we mean in the math department by quadratics? What function is quadratic? Exactly quadratic. A(n) squared plus bn plus c, right? Again, I don't like a equals 0. So let's not have it, a equals 0. Because if a is 0, then what kind of function is this? Linear. So that's why I want to be clear. It's linear or quadratic. I don't like, if quadratic becomes linear and linears become constants. Okay, so guess what we're going to mean by quadratic in CS? Asymptotic. Quadratic. Same mechanism. Yes?
So the square root of n is not asymptotically.
F of n, it doesn't have to be quadratic, right? It's smaller than some quadratic function, and it's bigger than some other quadratic function.
I was asking if the other, so that's not asymptotic.
What?
The first example.
This one?
Yeah, that's not counted as asymptotically linear.
That's not linear because this inequality doesn't work. I just showing here that if you go far enough towards infinity, eventually this number will beat that number. So as an exercise, any a coefficient you pick, I pick a equal 10 to the minus 6, eventually a times n will be bigger than the square root of n. Think about it. A(n) versus square root of n, even if a is very small. A(n) is going to look like a line, right? How about the square root? Square root is going to bend this way, and the line is going to go that way. So eventually the line is going to be the square root. So how about 3n squared minus log of n plus 5n plus cosine of n? Is that the quadratic function in the CS definition? Yeah. It's smaller than 4n squared and bigger than 2n squared. At some point. Of course, in the beginning, it doesn't work. If you put small values of n, it doesn't work. But we don't care about the beginning. We care when n goes really big, like into the 10 to the 12, 10 to the 100, 10 to the 1,000. When n goes really big, these guys are losers, right? They don't really do nothing in here. This guy is the guy that dominates everything. Right? Think about even like 1,000. Add 1,000, how much is log of 1,000? How much is 5 times 1,000? How much is cosine of 1,000? It's nothing compared to 1,000 squared, which is 1,000,000. Right? The point is this is going to dominate, and this is between 2 of those and 4 of those, so that's right? Quadratic function. Again, you may be incorrect when you say that's quadratic if you talk to a mathematician, but be careful and put the word asymptotic quadratic. So you know, cover your trail there. So that's what we mean. And how are we going to call this? Data of? How about exponential? Let's call it base 2. 2 to the n, right? That's the exponential mathematical function. What is for us in CS exponential asymptote? Base matters here. You can't just say exponential. You have to say the base. In here, you don't have to specify the coefficient like 3n squared. What do we call a function to be exponential? It has to be between 2n plus something small and 2n plus something small. By small, I mean not exponential. So for example, a function might be 2n plus n cubed and 2n plus n to the 7th. clearly there's space between n cubed and n to the 7, right? To put some things in there. That function we're going to call theta of 2 to the n. Asymptotically 2 exponential. Exponential creates 2. Because it's between two functions that are dominated by the 2 to the n exponent. It could be even a constant in front of 2 to the n. Like say this is 1/2 of 2 to the n, and that's a better definition actually. Let's say that's a constant, say C1 times 2 to the n, and this is C2 times 2 to the n. For example, this might be 2 times 2 to the n, and this might be 7 times 2 to the n. It's a constant here, it's a constant here. Those are exponential base 2 times a constant, exponential base 2 times a constant. Therefore, that's it. So that's going to apply for all functions. What does it mean to be following this idea? What does it mean to be theta of log n? It's in between some constant of a logarithmic function and some other constant of the logarithmic function. That doesn't mean the function itself is logarithmic. The function could be log n plus 1 over n plus 1 over n squared, which is not a logarithmic function. But it's definitely smaller than 3 logarithms and bigger than 1 logarithm, right? And because it's between 2 logarithms, we call it logarithm anyway. Because it has some other terms that are insignificant to the logarithm. These guys go to 0, you know. How about the square n? Is the square n a logarithmic function? Can I say the square n is smaller than some constant times the logarithm and some bigger than constant times the logarithm? Is there some constants that I can put here to say square n it's bigger than some logarithms, smaller than other logarithms? Is this one working? This inequality? Can I put a constant such that square n is bigger than the logarithm? What constant? Truth is I can put any constant. It's going to work. But let's say C1 equal 1. Is it true that the square root is bigger than the logarithm? Well, you guys should know this from high school.
Yeah.
Square root of n is still a polynomial function. It's n at what power? 1/2, which is a fixed power. It's less than 1, but fixed power. Logarithm is not a polynomial function. So logarithm is going to lose versus any polynomial. Even n at 0.0001, which is a fixed exponential constant, will be bigger than a logarithm. But how about in here? Is there a constant that the logarithm, if I put C2 equal 10 to the 10, huge constant, can I get the logarithm to be bigger than n at a half? This is n at a half, right? Can I? Is there a constant that will make this work? No. There is no such constant. N at a half will beat any logarithm eventually if n is big enough. So I can't say square root is like a logarithmic function, aka between two logarithms. Because it's bigger than a logarithm, that works, but it's not smaller than a logarithm. Remember, you have to have logarithms on both sides to make it work? Yes.
Do you need to specify the base of the logarithm in the same way you specify the exponential?
This is true for every base.
Yeah.
But you can specify the base. When I say log, I mean base 2. When I say ln, I mean log e. When I say lg, I mean log base 10.
Okay.
But for any base, which is fixed base, we'll have the same problem.
Okay.
Even if you put log base 3, 5, 10, 11, 100, still the logarithm cannot beat the square root on any base. Logarithm is just too slow of a function to beat the square root. Remember, square root is still n at a fixed power. It doesn't look like a polynomial, like n to the 2 or 3 or 4, but it's still a fixed power. Logarithm is not. It has to do with the fact that it's the inverse of the exponential function, so it's going to lose. Just like every exponential function is going to beat any polynomial of any degree, the opposite is true. The logarithmic, which is the inverse of the exponential, is going to lose against any polynomial. Eventually. Okay? So that's what I have to say about what we call things in computer science and what we mean by it. What happens if those things happen only on one side? I have a function. It's less than a linear, but I can't prove the left side. I don't know if it's less than a linear or not. Maybe it is, I just don't know. I can't use theta, right? Theta means it's between two linear functions. So what if I say just this part? How do I say, okay, I know it's smaller than a linear function, but I don't want to say more than that?
Say O of n.
Oh. So O of n is half of theta. If I can put it between two linear functions, just smaller than a linear function. So it very well happened, you know, I teach a lot of algorithms classes, and the answer is theta of n. Some students can get the theta because they get the upper bound and the lower bound. And some students only can prove the upper bound, so they say O of n. So this has to do either with what we can prove about that function, or with how much we know or how smart we are. You know, maybe there is a way to show it's bigger than a linear function. We can't just do that, so then we leave it at that. O of n is just this. How about this part in here? If I can only show it's bigger than a linear or equal to, but I can't show the upper bound, how do I write that?
Omega.
Omega. So this is not the omega from probabilities, right? Just to be clear, it's a different omega. If you can, theta is the best. If somebody asks you, how is this function behaving, growing? Theta is the best way to do it. But sometimes we can't. Sometimes we say, I'm not sure, but I know it's at most a linear. At most linear. And this is saying, well, I don't know the upper bound, could be anything, but I know it's what? At least linear. So linear or bigger. How about in here? If I can only prove one side, if I can only prove this is smaller than this part in here. A quadratic is smaller than f, but I can't prove the right side. How would I call this part? F of n is same like in that. I can't do theta of n squared because I can only prove the back inequality, the left side. So this is theta of n squared. And if I can only prove the upper bound, I'm going to call f of n is O of n squared. So again, theta is the best. It gives you both the lower and upper bounds. It's like smaller than a quadratic, bigger than a quadratic. It's kind of like a quadratic. If you can only do one half, you say O of n squared. It says, I know it's not bigger than a quadratic function, but it could be a lot smaller. So back to my example here, is square n. I can't prove theta, right? I said one of inequalities doesn't work. Which one I can prove? Is it smaller than a linear or bigger than a linear? So which one I prove? O of n. It's not bigger than a linear. It's linear or smaller, but I can't prove the theta because this doesn't work out. Hands up who's with me. All right. This is how we're going to talk about those things, and as we keep talking, this is going to become more mathematically interesting and more formal. For now, you only need to know this basic idea. When I say something's linear, it doesn't have to be linear. It just have to be upper bounded and lower bounded by linear functions. If I say at most linear, I only mean the upper bound. I don't know how small it is, but certainly not bigger than a linear function. Data structures. What we need to do really quick is arrays and lists. Just for recap purposes, when I say array, I mean here's the values 6, 3, 7, 2, 4, 5, 1, 8. But what I truly mean by an array, I can access A of 3. That's called random access. I can call the array directly, give me the third element. And everybody knows how does this happen in memory? How can I do that? How computers can represent arrays so you can get directly access to the third or fifth or seventh element? What does it need to happen in the memory? How can I store an array so that when the programmer says, I want the fifth element, I know exactly where to go and find it out? I have to use an index, but how is the array has to be organized in memory?
Continuous.
Continuous chunk of memory. Because if you look at an array, it takes a bunch of memory bits. How many bits for the first element? How many bits the second, third, fourth? It knows if this is the beginning of the array, then it knows exactly where to jump in memory to find the fourth element or the fifth element. It knows how many bits are per element. It knows you want to jump to the sixth element. Does the calculation, 6 times how many bits you have, 32 bits per element. It jumps exactly to this memory address to find that. Okay. In a list, there is no random access. There is some value and some pointer to the next value, some pointer to the next value. But those objects can be anywhere in memory. All I have to do is a value that could be the same value, 6, 3, 7, 2, so on and so forth, and a pointer, a memory address for the next value, which could be somewhere else in memory. It doesn't have to be non-continuous. So in a list, I don't have random access. I can't say, give me the fourth element. I don't know where to go to find the fourth element. The only way, this is the head, the only way to go in a list is to go from here and say, you want the fourth element? Okay, that's the first one. Go to the second one, go to the third one, go to the fourth one. That's how I get to the fourth element. There's no way to say, here's the memory access. Of course, I could store the addresses. But if I store the addresses, I effectively got an array now. If there's a way to get directly to the fourth element, better use an array. Those two are the basic data structures. But then, of course, there's a lot more. Stacks, queues, heaps, trees, graphs, skip lists, NRE trees, and some other ones. A lot of stuff built on top of those two data structures. Networks. And you're going to study them until you finish your degree. When you graduate, you're going to see a lot of these data structures, especially in the algorithms course. But these two are the ones that we need the most. So that's an overview. Let's start the searching and sorting procedures. And we'll do the basic ones today. And then we'll see Friday where we are. So remember, it's very important in a problem when you are given, say, a bunch of values, or you are given something to look for or something to be organized, you have to determine. In some problems, it's clear from the text, but you have to determine whether the data structure is given or you have to decide. Suppose I'm telling you, you have to sort the students by their midterm grade. That means probably that you can choose whether you represent the students with an array or with a list or something else. But if I say there is a list of students with their grades, you have to work with a list. If I say there's an array that contains, people's salaries, you have to work with that array. So you have to know what kind of data structure you're given, because algorithms depend on the data structure. The same algorithm may not work with a list and an array. Some problems, they say, organize it. Here's a data input in a file, and you choose whether you create an array or a list from that data structure. So then it's good, because you get to choose the data structure which gives you the options you want for the algorithm. But if the data structure is given, like you have an array, you stack with that array. Okay? So searching. The stuff that everybody knows is linear or sequential. Works in both array or lists. Everybody knows what this means? I do a sequential search. So I have a as input, I have a data structure A, and I have a value I'm looking for. A value looking for. What does it mean to sequentially look for this value or linearly look for this value? Yes.
You take a look at every value and you compare it to the value that you're searching for.
So I look into my array. This could be a list or an array, and do what?
You go through every element starting from the first value and compare it to the one that you're searching for.
Right. So if my array is, say, A1, A2, up to AN, which I'm going to call, in terms of pseudocode, A of 1, A of 2, because remember I can access every element. How do I do the pseudocode here? For I equal 1 to n, loop, if A of I is equal to the value, bingo. I want, sometimes I write bingo. I mean the students have to replace bingo with what needs to happen. When I found that value, you have to print it, da-da-da. But what we need to write, if we say bingo, something like, okay, we're done. How do we actually say done?
Return.
You have to say here, terminate. Or return. Or break or stop or something like this. What I mean to say, you could leave here this bingo to say, okay, bingo really means print that on the screen or send it to my friend or crash the computer or do something, okay? That's okay with me. If you don't want to deal with what happens right there in the middle of procedure. But you have to say whether you terminate the program or not. Are we terminating in this case? Or we keep going? We are in the middle of a loop here. If I found the value, am I, after the bingo part, print the value, am I done? Yes. So that's why I'm going to terminate. And if not, what? Do I have to do anything here? Do I have to say I equal I plus 1? Why not? Because the for loop controls the I. When I say for I equal 1 to n, this already implies 1, 2, 3, 4, up to n. So I don't have to control the I equal I plus 1. Where would I have to do this? In what kind of loop I have to put I equal I plus 1? In a while loop. While loop does not control the next mechanism. While loop says, while some condition didn't happen, it's not going to increment the I for you. But in here, I don't need to do this. Do I have to do anything? What happens if I exit this loop without terminating? I run through the array. I never got to the bingo part because I didn't find the value. Then what?
That means the value you wanted was not in the array.
So I have to do something like print not found. Easy, right? Can I do this with a list? I can do it, just not this way. In a list, I can't say if A of I, because I don't have access to A of I. So how do I do this with a list? Yes, I start with A equal head.
I would say while there's a pointer to the next.
While I'm going to put here a question mark, that means you guys have to fill that condition. How far I go. And then it's a loop, right?
Yeah.
What do I do?
Then A equals
Value.
B.
is B. Bingo. Again, you have to replace bingo to what you need to do when you found it. Do I terminate?
Yes.
Terminate, stop. And now I'm in a while loop. Do I need to control my mechanism for the loop? In here, I didn't have to control it because the for loop jumps next iteration to the next I. But in here, how do I control it?
A equals A dot equals B.
There's gotta be a way to go to the next element in a list. In a list, there is a mechanism typically called next that just moves you to the next object or element in the list. If it's not next, you call it future, you can call it advance, whatever. There's gotta be a way to move to the next element. So if I'm out of this loop and I didn't stop, what do I have to do? Print not found. Hands up who's with me here. Okay, any questions about it? Linear search means go over every single value. When you found it, stop. If not, move on. But be careful how you move on. In an array, you have the for option. In a list, you just have to move to the next element. Okay, that was good. How about the runtime? I'm moving to one of these columns here. How long does this take? There is two kinds of runtime. There is the worst case, and there is the average case. That's our friend, expected values. And there is a best case that we don't really care about. In computer science analysis, you can be very lucky, but we can count on that lucky, unless there is a reason to believe it's a high probability to be lucky. The names coming from the registrar are very likely to be sorted, and that's a lucky case. If I know it's likely, then okay, I can count on being lucky. But typically, unlucky or lucky, it's a rare case. So what's the worst case in here? Yes.
That the element you want is all the way at the end of the array.
The worst case is that it's not there at all, right? But either way, either it's at the very end or not there, how many steps gonna take in here? Yes. How do we judge that? Is n loop iterations, right? Times how much an iteration takes. Following my ideas here with O of n, who would you think is theta of 1? Sorry, theta. So remember what theta means? It's between two of the same kind. It's smaller than a constant, and it's bigger than a constant. Any constants. The point is it has to be some constant if it's between two constants. How about O of 1? Has to be smaller than a constant. And has to be greater than 0. All the functions you deal with are greater than 0. Because the runtimes, everything will take at least 0. So theta of 1 and O of 1 are the same. They're the only case where they mean the same thing. O of 1 or theta of 1 means it's a constant we don't know. It might be 100, it might be 20, it might be 12.5, it might be a million, but there is some constant. So can I say each loop takes roughly theta of 1? It's a constant time operation here. I don't know how many seconds that is exactly, but can I say this is a finite number of steps, they're always going to happen in every iteration? So how much is this? Theta of n, right? Because it's n times theta of 1, it's a linear function. How about in here? Worst case, theta of n. But on average, if there is an equal probability that my value is either 1 or 2 or 3 up to n, what's the expected runtime? That is the average case. Well, it could be the first one. The probability of that is 1 over n, right? If it's the first one, I go through how many iterations? 1. If it's the second one, I go through how many iterations? 2. And what's the chance of that? 1 over n. If it's the third one, it's 1 over n. If it's the last one, it's 1 over n. Right? So this is, if it's the first value, I go 1 iteration. If it's the second value, I do 2 iterations. If it's n value, I do n iterations. If it's not there at all, I do n plus 1 iterations. Maybe that's also blended in. 1 plus 1, 1 plus 1, 1 plus 1, 1 plus 1, 1 plus 1. So this is looking like 1 plus 2 plus 3 plus 4 plus 1 plus 1 divided by 1 plus 1. Right? That's an average. He's saying it could be the first one, the second one, the third one, or none at all. There's all these n plus 1 cases, all with probability 1 over n plus 1 because we assume uniform distribution. I don't know how to compute this function, right? I didn't study series and all of that. But can anybody make a guess in terms of theta? Yes.
N over 2.
Theta of n over 2, you say? I say that's the same as theta of n. Because it comes down to being a linear function. Theta of n or n over 2 mean the same thing. It's between 2 linear functions. It's theta of n is theta of n over 2. Theta of n over 5, theta of 3n, they all mean linear. Can everybody see that this is between 2 linear functions without doing the actual calculations? Is it clearly bigger than, say, half of n or a quarter of n or something like this? Is it clearly less than, say, 3n or 5n or 7n? I mean, I don't say it's obvious, but you should be able to say, why is this between 2 linear functions? Say, for example, this is smaller than 1/2 of n or 1/4 of n, and bigger than 3n. Smaller than 3n, bigger than 1/4 of n. If I show this, according to my definition, is theta of n, right? Between 2 linear functions. Without doing the exact calculations. Of course, next week, we'll do the exact calculation of how to calculate this exact. And we'll see, indeed, it's a linear function. All right? How about if the array is sorted? So I have an array here. A of 1 is smaller than A of 2, is smaller than A of n, and I'm searching in that array for some value. What then? I can do linear search, because I can do linear search in any array, but this one's sorted. So can I do it faster? Yes, because we already did it, right? How is that called? Binary search. How does that work, binary search? Yes. Yes.
So you check if it's in the first half or the second half and like cut off chunks.
How do I check if it's in the first half?
You pick the center element and see if it's greater. or
Pick
less
the
than
center element, that is the beginning, say b is 1, the ending is n. I do b plus c divided by 2, right? That's kind of the middle element. And then he's saying check if my value is smaller than the center, a of m. It means, where is this value now? I look at my array and I chop it in half. This is m, this is the left side, and this is the right side. If the value is smaller than this, since it's sorted, it's guaranteed to be in here, right? So I want to go here, go in left side. Else, actually, I should do strictly smaller, is strictly bigger. I want to go right side. And else, if it's neither bigger or smaller, I found it, right? Bingo. Can I stop if I found it? I found it. Well, what do you mean go in the left side? How do you go in the left side here? Instead of having from the beginning, beginning B to the end, what is my beginning and end now if I go to the left side? B remains B, right? And who's E now? And go to the right side means the end remains N, and the beginning must be now M. So if I want to go on the left side, I keep the B in the beginning and I move E to the middle. Now BE is the left side. If I want to go on the right side, I keep the B at the middle. I move the B in the middle, keep the E here. Now I have the right side. And this has to be a loop, right? Go in the left side means keep doing it. Just not in the whole array, just the left side. So I need a loop here. What kind of loop? Is it a while loop, a for loop? It's a while loop. After setting B and E, you get to, again, write the condition down. And do I need to do something here? I already set the middle. I decided E is M or B is M. And in here, I don't have to do anything. Just I have to figure out when this terminates. Either when I find the value, of course, or how do I know it's no point going any further? Yes? B and E are very close, either consecutive or the same value. There's no point trying to chop it in half, right? So the condition has to be related to how close B and E are together. Well, how do we analyze this algorithm? How many, can we say the internal is still a constant amount of time? The number of what happens inside the loop. It's a comparison, another comparison, and a statement. Is that a constant amount of operations? Like 3? That's a constant amount of time. But the question is, how many times is this going to loop? Right? How many iterations? Because in here, how many iterations we had? N, right? In here, do we have N? What happens with each iteration of the loop? Yes. Yeah.
You're working with half of the stuff every time, so
Right.
it will be like half of the.
So in the first iteration, the size of the array, effective size, is N things. But in the second iteration, it's what? The effective size is N by 2, right? Either I go to the left side or right side. Either way, the effective array I'm looking into is just half of the original size. How about the third iteration? It's going to be N by 4. How about at the kth iteration? It's going to be N by 2 to the k minus 1. Same? So what's the last k? What's the last iteration? When is this going to stop? When the size of it is approximately, when B and E are the same value, means the size of the effective array is what? 1, because it's just one element. So then k has to be approximately how big? N divided by 2 to the k has to be 1. So how big is k?
Log base 2.
Because you solve this equation, 2 to the k is n, that means k is log base 2 of n. So how many steps is this going to take? Log base 2 of n. So this whole thing is theta of log n. Because it's n iterations, and the amount in each iteration, how much work is being done, is a constant. Like 3 steps, 5 steps, times log n is log n function. Again, what does this mean? It's not really logarithmic. What it means it's between a big logarithm and a small logarithm. That's what it is. it might be some other things in there. So that's binary search. Can I do it on a list? Can I do binary search on a list? Why not?
Because you can't access the center rules of everyone.
I cannot access the center of a list. I can do b plus c by 2 if I want to, m, I can compute m, but I can't get the value of the list in the middle. Remember, in a list, there's no way to access some element in the middle. You have to go from the next from the beginning. So I can't do binary search in a list. It has to be an array. Maybe there's a fancy data structure like a list, skip list, or a tree, or some stack, or something that still I can do binary search on, but on a basic list, I can't access the middle or any other element directly. I have to go from the top, which prevents me from doing binary search. There is this thing called chunk search in the book and in your homework, which is not very well written in the book. So let me give you a good version of it. Chunk search, you could apply it to a sorted array, but you should not really apply it to a sorted array, because in a sorted array, binary search is optimal. We can prove that this is the best time you can search for things. There's no way to do it faster than this. In fact, what would we compute here? Worst case, or average case, or best case? When I say there are n iterations maximum, each of them on a constant amount of time, I was referring to worst case or the average case? Worst case, right? Is it possible to finish earlier than all iterations? Definitely. So what is the expected of binary search? That is, there is an equal probability that my value is here, or here, or here, or here, anywhere. And I may be lucky early on, maybe I find it. I'm finishing one iteration, or two or three. That's your exercise, star. It's still log n. So even in average, you still will do log n. Or approximate absolutely log n operations. So here's an exercise. Chunk search. Items are not sorted, but organized in chunks, or piles, or groups that can be verified in, let's call the number of group k, in constant time. Think about somebody doesn't sort their playing cards, the deck of cards. How many cards are there? 52. But he puts the clubs, spades, and hearts, and diamonds in 4 different piles. So now you're looking for the ace of diamonds, say. You can immediately pick a pile. You have the pile in front of you. You can pick a pile, open a card. If you see a club, what do? You ignore that pile. In one operation, you decided that's the chunk I want or not, right? Think about somebody has cars, they're not sorted. You're looking for a particular car, you're the police. You have the plate number, the model, everything. And the parking lot organizes all Toyota to the left, all Fords to the right, all the Chevys in the middle. Now, you open the door to the first garage, and if you see Chevys, you know you're looking for a Toyota. You don't have to look to that garage, right? Because that's all Chevys. Makes sense what I'm saying? So they are not sorted, but they are in these piles that you can check immediately what pile is it. So I have n items organized in piles. So what am I gonna do? Check linear search on piles So I have to check where is my Toyota. Check the first garage, second garage, third garage until I find the garage with Toyotas, right? That how long is that gonna take? If I have K groups, K garages, K. And then once I found the right file, on the right file, do a linear search on the items. If they're uniform, each file has about n by k items, right? If those happen to be organized in piles of equal sizes, how long is this gonna take? Now that I found the right garage, I'm gonna look to the cars in that garage. That's gonna be n by k, because in that garage, in every garage, I'm expecting about n by k items. So what's the total? K plus n by k, roughly. What is the best k to minimize this function? If I want the minimum total for a fixed n. Suppose n is fixed, I have 1,000,000 cars. What value of k will give me the overall minimum? Because I have to search for the right garage, that's k, and then it's a garage, I have to search for the right car. Now if k is very large, k is 1,000,000, just looking for the garage is going to take like a linear search through all items. If k is very small, I'll find the garage very quickly if it's only 1 or 2 garages, but then I have to look through a lot of cars in that garage. So what k will make this exercise? What is the minimum k that minimizes k plus n by k? Anybody knows the answer to that? For a fixed n is fixed in here. What k realizes the minimum of this function? It's a quadratic equation that we need to minimize. Anybody has a guess what's the minimum? Yes.
Square root.
Yes. So we call that in mathematics as minimum because we want to minimize, but we're looking for the argument k, not for the body. Try to prove that the minimum of this function is square root of n. All right, so we didn't do sorting. We'll have to do sorting next time. So we did searching and there's reduction.
No, I